All right, welcome back. Dr. Pitcher here with the next lecture in Chapter 5. And in this lecture, I'm going to talk about a few different concepts here, which relate a little bit to the lab, but also to stereoisomers in general. I'll talk about racemic mixtures, optical purity, and enantiomeric excess. So let's start with a few definitions here. So a racemic mixture is a 50-50 mixture of enantiomers. Okay, so these are my enantiomers, and I've got a mole of this and a mole of this, and mixed together, that is a racemic mixture. Okay. Now, an interesting thing about racemic mixtures is that they are not optically active. In other words, their specific rotation is going to be 0 degrees. So just to revisit here, I'm just going to put this up for just a minute here. We talked about in Lecture 2 specific rotation. And we define that by the observed rotation in degrees using the polarimeter divided by the path length times concentration. And if we have a neat substance, no solvent present, we can just use the density instead of the concentration. We choose the path length to equal 1, or we use a path length that equals 1 decimeter, so that's just 1 there, so it ends up being observed rotation divided by concentration or density. That's your specific rotation. Now, specifically, that specific rotation is the observed specific rotation. And you could look up in literature, in the Merck index, for example, you could look up a literature value for the specific rotation for a given chiral optically active compound. So that brings us to the concept of optical purity. So our percent optical purity, I'll just abbreviate that, OP, is going to equal our observed specific rotation divided by the specific rotation of the pure compound. So that's going to be our literature value. And then times 100 to convert it into a percentage. Now, if you had an optical purity of 100%, then you would have 100% of that enantiomer. If you had an optical purity of 0, you'd have a 50-50 mixture of the enantiomer. Now, that leads to the next, the next term I want to define, which is enantiomeric excess. And so this is how much extra of one enantiomer is present in a mixture of enantiomers. Okay, and so our percent enantiomeric excess is going to equal our let's see, our amount of, so we'll just say our percent, we'll say percent I'm not going to call it R, I'm going to do percent plus enantiomer minus the percent minus enantiomer. So the difference between the two, and we'll take the absolute value of that, and then we'll divide that by the percent plus enantiomer plus the percent minus enantiomer. And then that's going to be times 100%. And one thing that's important to realize is that optical purity, or percent optical purity, equals our percent enantiomeric excess. So you would measure an observed rotation, compare it to the literature value for the pure specific rotation, and convert that to a percentage. And then that's your enantiomeric excess. So let's just say, as an example, let's say, for example, what is percent EE of a mixture that is 75% plus and 25% minus. So our percent EE equals 75% minus 25% divided by 75 plus 25 and times 100%. So that's going to equal 50% over 100% times 100%. My percents cancel, or my 100% cancel, and I get 50% enantiomeric excess. What this is really saying is that if we look at our mixture, part of the mixture is racemic. So in this case, we've got 75% plus enantiomer, 25% minus enantiomer. So if we took out the 50% excess plus enantiomer, we would have a racemic mixture. So enantiomeric excess is not how much of a given enantiomer is there, but how much extra of a given enantiomer is there. Okay? And this is important when you're actually doing the lab. The concept of a racemic mixture is important because we'll see later on, when we look at certain reactions, we get what is called racemization, where we might start with something that is chiral, and we may have a starting material that is chiral, but in the process of the reaction, we end up with a product that is a 50-50 mixture of enantiomers. We call that racemization. And so it's important to understand the concept of a racemic mixture. All right. So hopefully that helps fully understand some of the lab. And until next time, stay safe out there. Bye now.